In January 2023, the entire U.S. air travel system ground to a halt. Thousands of commercial flights sat frozen due to one corrupted database file. We spend our time focusing on sleek app interfaces and clean front-end code, but behind every button click, there is a hidden system organizing our reality. Writing a piece of information to a disk is trivial, but structuring, retrieving, and scaling that information so millions of people can access it at the same time without data colliding is a massive challenge in computer science. These databases act as the active logic engines that dictate exactly how modern civilization operates. The first major crisis of scale hit the United States in the 1880s. The census had grown so massive that human clerks couldn't count the data fast enough. By the time they finished, the demographics were already 10 years out of date. To fix this, an inventor named Herman Hollerith built an electromechanical tabulating machine. By using spring-loaded pins to close electrical circuits through holes punched in paper, machines could read and calculate data automatically. Hollerith borrowed this concept from the textile industry. In 1801, Joseph Marie Jacquard automated weaving using these punched cards, creating the first binary storage medium. This mechanical system processed the 1890 census in just 2 years, saving the government millions. Hollerith's company eventually merged to form IBM, establishing a physical storage method that would dominate the next 70 years of computing. By the 1950s, heavy cardboard gave way to magnetic tape. But tape had a significant bottleneck: linear sequential access. To find a single customer record, the computer had to physically spin miles of tape from start to finish, a process that could take hours. In the 1960s, Charles Bachman introduced the network model. It gave data structure by linking records together via hard-coded directional pointers, allowing the computer to jump between specific memory addresses. American Airlines used this architecture to build Sabre, a massive reservation system running on dual IBM 7090 mainframes. It processed 80,000 daily calls and dropped booking times from hours to seconds. Navigational systems carried a hidden risk. Whoever controls the query path, like an airline burying its competition, effectively controls the market. These early databases were also incredibly brittle. If a developer needed to add a new category of information, the physical memory pointer shifted, instantly breaking the thousands of lines of code that relied on those exact paths. In 1970, IBM mathematician Edgar Codd proposed a fix: the relational model. He organized data logically into mathematical tables, a clean grid of columns and rows. This allowed for SQL, letting developers simply describe what data they needed. IBM hesitated to commercialize Codd's ideas to protect its older mainframe business. This allowed Larry Ellison to build the first commercial SQL database for cheaper mini-computers, launching Oracle. The relational model and its ACID guarantees standardized corporate computing, creating a universal template for how businesses processed information for decades. Then the web arrived. By the early 2000s, web applications were attempting to manage petabytes of unstructured data. The massive SQL servers designed for single offices began to crack under the pressure of millions of simultaneous users. To survive, Google and Amazon abandoned perfect immediate consistency, distributing data across thousands of cheap commodity servers. This NoSQL movement traded absolute certainty for massive horizontal scale, keeping systems online even if momentarily out of sync. By the 2010s, monolithic engineering teams hit another wall trying to manage these massive datasets. This led to data products, where individual departments own their data through clear contracts rather than dumping it into one unmanaged lake. Planetary scale changed the requirements of data architecture. For the largest systems, absolute consistency is now a luxury, often exchanged for the ability to serve the entire planet. Today's challenge is artificial intelligence. Neural networks don't look for exact keyword matches. They require deep semantic context to understand how different concepts relate. A vector database translates raw information into high-dimensional coordinates. Concepts with similar meanings gravitate in mathematical space, indexing actual meaning. This is polyglot persistence. Modern applications route incoming data to specific engines, optimized for speed, transactions, or context. Data systems have decoupled from hardware limits, existing as a self-healing cloud layer that handles 2.5 quintillion bytes every day. From the 1801 loom to modern neural networks, We have always tried to organize information so machines can act on our behalf. The storage mechanism is just a tool, but as the Sabre system proved decades ago, the architecture of that tool dictates how information flows, who sees it, and who holds the most power.